Okay, I think it's time to start. Good morning, everyone, and welcome to this second day of IBIC. I am Nicolas Hubert, and I am pleased to chair this first session. Just before we start, I have to say a word about the proceeding. We would like to thank all the authors who have already submitted their papers, but we have still something like 25% of the papers which haven't been submitted yet. So we would like to encourage all the authors to do it as soon as possible. And for the papers who are already submitted, the large majority of them are already in a green status, so ready to proceed. Thank you very much for that. There are still some of them which are in yellow or red status, so the proceeding office is waiting for an answer from the authors. So please check your emails and check the status of your papers. Thank you very much. So this morning, the session will deal with beam position monitors and machine parameter measurements. We'll have 2 invited talks and 1 contributed. We also have 10 minutes available for discussion, and we will split this time in between the talk in order to have more time for questions. The first speaker this morning is Professor Stefan Gibson. He is the head of the Department of Physics at Royal Holloway University of London and the Deputy Director of the John Adams Institute for Accelerator Science. He leads the accelerator group at Royal Holloway and has a background in experimental particle physics and detector instrumentation, especially optical systems. His research focuses advanced instrumentation to determine properties of intense hadron beams. He leads the UK diagnostics work package for the high luminosity LHC and collaborates with CERN beam instrumentation to develop electro-optic beam position monitors. His team built the transverse laser wire emittance scanner for the hydrogen ion beam of LINAC 4 at CERN and is currently implementing a novel laser wire at the front-end test stand at Rutherford Appleton Laboratory, UK. Prior to joining Royal Holloway in 2013, Stephen was a CERN Marie Curie Fellow, where he studied the electron performance of ATLAS, electroweak physics, and radiation damage of the pixel detectors. And this morning, Stephen will talk about electro-optical BPM development for high luminosity LHC. Please, Stephen.
Okay, well, thank you very much for that very long introduction. That's very kind. Short CV, really. But I'd like to first begin by thanking the organizers for this kind invitation to give the talk. We're very pleased to present this work on behalf of Alberto and Thibaut and Tom. Talking about electro-optic beam position monitor development for the high Lumi LHC. So I'll begin with the motivation of why we're developing these diagnostics, both for high Lumi and in general for fast diagnostics for future accelerators. I'll introduce the concept of the EO BPM, the basic principle, but also focusing on the interferometric design that's the current baseline now for high Lumi LHC in terms of this development, and also the historic developments that have gone into this work. And then I'll focus on simulations of an improved design based on a lithium niobate waveguide and validation of that design in recent beam tests last year at the HIRAD-MAT facility, studying the transverse resolution of the device, and then also bandwidth resolution studies that have just begun this year at CLEAR, and then with a focus on future developments too. So we all know the LHC. It's equipped with a vast suite of beam instrumentation. So what's really changing, of course, at high Lumi is the addition of the crab cavities, among many other upgrades, but the crab cavities that rotate the bunches close to the just before the collision point, so that it improves the overlap between the colliding beams. This allows us, of course, to enhance the interaction rate from around 23 interactions per bunch crossing up to around 140 at high Lumi LHC. So this crabbing of the bunches is something that we need to monitor, not only the crabbing itself, but after the crabbing, does it come back to being exactly parallel to the propagation direction of the beam, and are any instabilities introduced. So we want to measure this with extreme sensitivity. The current system within the CERN complex to monitor head-tail instabilities is the CERN head-tail monitor. So this is a strip-line BPM design, which is long enough to separate out the signals coming from the reflection and the incident signal. I think this is the PDF, so the animation is in the PowerPoint that's uploaded. But it's a very clean time domain signal that it's extracted from such BPMs, and indeed this was the device that was used to measure the first crabbing of a prototype crab cavity that produced a crabbed bunch in the SBS back in 2018 that you can see down on the right-hand side there. It's a funny system down there. Okay. So the EOBPM project has grown out of the idea to upgrade the head-tail monitors of the LHC and to visualize these instabilities. The bandwidth of conventional diagnostics like the strip lines is still limited to a certain extent by both the pickups themselves, but also the hybrid in particular that combines the signals and generates the difference in some signals, and also the very long cables that go up to a fast sampling oscilloscope. And so the idea of this development is to replace the capacitive pickups with electro-optic crystals that can respond extremely rapidly to the passing bunch, and also to replace the electrical cables by fiber optic readout, so you eliminate any electric noise from the accelerator, etc., on the cables. The aim of the project is to develop a reasonably high bandwidth device, so we'd like to be able to measure not only the head-tail, but all the various modes of instability of the bunch. If we go up to mode 6, that would require a resolution of better than 100 picoseconds, and higher bandwidths are required for the higher order mode. So typically we're aiming at sort of 6 to 10 gigahertz at the upper end, but it's a very broadband device along this 1 nanosecond bunch. So we're really trying to measure the transverse position along the bunch. The basic principle of the EOBPM is shown here. So the idea is that you have, as I mentioned, the crystals replacing the capacitive pickups. We send light that's polarized through the crystal, and as the field of the passing bunch interacts with the crystal via the Pockels effect, you have a change in polarization state of the light that is transmitted. And if you then, in the simple example, place an analyzer after that crystal, you can detect an intensity change at a downstream detector with a very fast photodetector. And of course, the advantage there is that you're eliminating any electrical connection. It's entirely optically powered and optically read out. So that's the original design that was actually presented at IBIC way back in 2015 down at Melbourne. Another concept that was also presented there was that of interferometric electro-optic BPM. So this is where you take the laser, you split it in fiber, and pass the light through both sides of the BPM. And the advantage of doing this is that you create a Mach-Zehnder interferometer with the crystals in each arm of that interferometer, and you're therefore sensitive directly to the optical difference signal, basically, between the two arms of the interferometer. So as the passing bunch moves along, it generates a phase change in both arms. If it's perfectly on center, then effectively you'll have a null interference at the detector, but if it's offset slightly, you will then detect that as an intensity change at the detector. And the advantage there is that you can directly encode the difference signal at your detector, and so therefore get a good resolution. Now, the studies that I'm going to present today are based on actually a triple interferometer design, where we have an interferometer not only between what we call the common mode, which is actually the difference signal between the two crystals, but also two side mode interferometers, which have one arm going through the crystal and one arm that bypasses the crystal and is unmodulated. And the idea here is that in the test that we were performing at high-rad MAT, we could assess all of the different interferometric signals. In the past, we've already shown at IBIC back in 2018 the interference around just one arm of one side of the BPM using the bypassed interference mode. But actually today I'm going to present for the first time the optical difference signal between the two sides. It's never been tested until now. So just a reminder of some of the historic developments. I guess Thibaut is somewhere in the audience standing here. So this is us in the tunnel at the SBS where the EOBPM was first installed. And this consisted in 2015 of a very bulky free space optics. So this box essentially that's attached to the beam pipe, so quite a bulky device. And over the course of several years, that system has been gradually miniaturized from being a bulky free space system to an in-fiber system that basically the splitting of the light happened in fiber, but then there was still a free space launch of the optics into the accelerator and then through the crystal and then back into fiber again. And now finally we've converged on a new design which is entirely in fiber. So the fiber is connected directly to an electro-optic waveguide that I'll discuss on the next slide, and it's all condensed and compacted down into a very small, neat pickup. So the original free space optics box that was tested at the SBS successfully demonstrated a weak proof of concept signal, but the real challenge operating there was that you're operating in a very large radius, 66.5 millimeters away from the bunch, which for electro-optics is, a very, very long distance compared to the pickups that you would normally bring extremely close to a bunch like an electron bunch that has a very short bunch length and therefore has a much higher field. So the field that we were able to get into the crystal at the SBS was relatively low, actually much less than 1 kilovolt per meter. So the optimization work that we've performed in recent years has focused on improving the field within the actual active part of the crystal, and we've developed a system that basically uses an electrode to condense that field and produce a highly magnified image of the Coulomb field as an optical imprint on the light that passes through the waveguide. So what you see on the right is is basically the electric field distribution as you move away from the bunch, just the normal fall off with radius. It drops to zero, of course, as it goes through the electrode, but then rises, or almost zero, then it rises very rapidly up to the point where the light is in the waveguide. And in the waveguide at that point, it's enhanced up to around 200 kilovolts per meter, so a very significant several orders of magnitude enhancement compared to what we were working with previously. So these waveguides have been developed in partnership with industry. So we're working with a photonics company in the UK to develop the waveguides. We've then inspected them in our nanofabrication clean rooms at Royal Holloway and manufactured them into a pickup at the Royal workshop, and then bench tested them at Royal Holloway on some RF equipment, VNA essentially. And then they were shipped to CERN, both for tests at high-rad MAT, which is the extraction line from the SPS, and also the clear facility to assess the bandwidth of the device. Here is just an overview of the shipment. So on the left you see actually this very beautiful real optical microscope image of the waveguide. So what you can see there, that very singular line in the center, is around it's about a 10 micron wide ridge of lithium niobate through which the light is propagating. It's a ridge waveguide which is very good at handling high powers, so you can increase the optical power going through the system and ultimately enhance your signal just by pumping more optical power. And that is embedded within the pickup shown below. You can perhaps just faintly make out the optical fibers emerging from either side. And just in the middle, we see the BPM effectively mounted on the bench test at Royal Holloway and attached to a VNA. So we pass signals through, simulating the beam signal through the setup, and then we've got multiple fibers that I'll explain in more detail in a moment that are taking the signals in and out of the BPM. That system was then shipped to CERN. It was aligned on a translation table that was shared with a Cherenkov BPM. That's the device shown with kind of the blue antenna wings behind it. So the EO BPM is at the front here. And of course, it was reception tested at CERN and then installed into the high-rad mat facility. So this picture is a little busy, but it basically shows the complexity of the setup, which is divided into three main areas. The laser source was housed in the control room, the BA7 control room. So that's shown here. So the laser, it's a Toptica. Well, sorry, it's a new focus laser source that's being pumped optically by a Toptica amplifier. And then we deliver the light down around 200 meters of optical fiber to the EO BPM, which is mounted on the extraction line in the foreground there in the middle. And then the readout is optical. We actually, just for convenience, we placed it in an adjacent tunnel for this particular device, but it could in principle go all the way back up to the surface or wherever you would like to place the acquisition system. Here's a closer view in the high-rad mat tunnel. The blue conical shielding is around the Cherenkov BPM, but you can see the electro-optic BPM in the foreground. And they're on a common table, so they can be translated across the extraction line of the high-rad mat. So this is a slightly more simplified setup that focuses on that common mode interferometer that's measuring the optical difference signal between the two arms. And what we expect is that, of course, this Mach-Zehnder interferometer, after passing, so the light split and passes around the two arms, but then it's combined at this biconic fused taper coupler that then splits the light into two arms. And of course, as with any Mach-Zehnder, you actually have an in-phase and an anti-phase signal that is then recorded by two photodetectors. In this case, we tested different photodetectors on the two different outputs just to assess the performance of different detectors. One was a detector that was then attached to a very high amplification stage. So it passed through a filter, but then had a 1 gigahertz 60 dB amplifier. The other detector was preamplified and just went through a 3 gigahertz filter. We're interested in this test not in assessing the very high bandwidth, but to just assess the signal strength at high-rad mat. And we also had some other detectors that we used for the side interferometer arms. So what you can see on the top right is the power distribution against time for those two different signals. So as the bunch passes by, you get basically a peak corresponding to the bunch profile with time. And that's as a result of the field being converted on what we call the transfer function. So you get a sinusoidal response of the interferometer as a function of the field that you apply, but we're typically working at a point on the transfer function shown here. So this linear region on the transfer function is where we typically set the working point by adjusting the wavelength of the laser to be able to get there. So here are some of the first results from high-rad mat. So we basically, on single shot extraction from the SBS, we were able to capture the signal passing through our EO BPM and measure the position of each individual bunch. This was done both for nominal proton bunch intensity, but also down to very low bunch intensities, actually as low as pilot bunches were still measurable. The plots shown on the right are for a slightly low proton bunch charge, around 7.7 times 10 to the 10. And what you can see is that as the EO BPM is translated across the extraction line, we of course get a linear response in position. So this is actually one of the first bunch by bunch position measurements that's measured electro-optically. The working point of the transfer function was set using an automated system where the laser makes a little frequency scan to assess where it is on the working point and then sets it to be at the optimum sensitivity position. So that was a useful part of the development. And the campaign was extended to several different runs. So as I said, this is for relatively low charge, and you see the in-phase and anti-phase signals. These are results for a slightly higher charge, closer to nominal. And as you translate the EO-BPM across the beam, you indeed see the anti-phase and in-phase signals basically shrinking or growing proportional to the distance across the beam. As you get very close to the pickup, you actually start to see signs of effectively saturation, where the bunch is causing such a field inside the pickup that it's causing an over-rotation of the transfer function. So this is why it's distorted at the very last one, because we've got almost too much signal for what we want. And indeed, you see that saturation if you go even further or use a much higher bunch charge. So in this case, if you follow the linear region too far, then you start to saturate the amplifier here. So we've got, in this particular case, too much signal, and it's saturating the amplifier that we had in this particular system. Okay. Then we move to the clear facility. So the same device was extracted from or taken out of the high-rad mat and placed into clear in order to use the very short electron bunches, which are only around 5 picoseconds long, and help to determine the time resolution of the system. So it was placed at the end of the clear on the in-air section of the beamline on a translation stage, and connected again via optical fiber to various different detection schemes. One was using the scheme that we had used at high-rad mat, but we also used a different optical probe, a 33 gigahertz optical probe from Keysight, attached to also a 33 gigahertz scope. So this allowed us to really assess the time resolution of the pickup response itself. And the other advantage of measuring directly with this probe was that we could determine not only what we call the AC modulation, which is the signal from the passing bunch, but also the point at which we were on the transfer function or the DC working point. So here are some of the first results from CLEAR. So just a preliminary analysis for today's talk, but essentially you can see that as a train of 5 electron bunches passes our pickup, we're able to see those as a sequence that's shown here against time, and the bunch separation here is measured to be 666 picoseconds. So that's the repetition rate of the machine. So nice confirmation that we're seeing the 5 bunches that were injected. And if you zoom in on essentially one of those bunches, you can see that the width is actually much less, or a little bit less than the 50 picoseconds that we were aiming for in terms of the specification of the design. So it's actually at the limit of what we were expecting this design to be. The pickup has a physical dimension, and that's compatible with a 50 picosecond time resolution. So that's good news. It's promising in terms of the pickup resolution for the future developments. And so speaking a little bit about the future, the focus now has shifted from that first prototype, which was an in-air prototype, to a fully in vacuum design. So the nice feature about the new design is that the optical part no longer has to be within the vacuum system itself. We don't need to send light in and out of a vacuum using any complicated vacuum feed-throughs. Instead, all of the optics is in air, and we have a brazed electrode design in a ceramic that essentially brings us the beam signal out and couples it into the pickup and into the waveguide. And so that's then detachable, so we can take that part off if we need to bake out the system, for example. So there's been some good progress in terms of the design. You can see the BPM CAD model that's shown here, and this is actually already in production, both at CERN and at Royal Holloway. I visited the company a couple of weeks ago, and we put together the first pickup for this new design. So this demonstrator is now being built and hopefully will be installed in the SPS and operated in Run 3, hopefully early next year. Okay. So I'd like to summarize. I mean, so far, the news really from this recent development is that we've measured single-shot bunches for the first time using an optical difference Mach-Zehnder interferometer. The signal strength has been significantly enhanced by using the electro-optic waveguide design, and also it's entirely in fiber. So there's no breakage in the system, and you can replace the cables with the optical fiber. In addition, the new electro-optic button shows a very good time response in the tests at clear. So within the 50 picoseconds time limit that was expected from the design of the system, and also related to the acquisition system available. But improvements in the bandwidth of the detection system are expected for the future prototype that we're now developing as an in-vacuum compatible design for the SPS. Okay, so I'd like to thank again the organizers for inviting the talk, and also for our colleagues at the HiRadMat team and also at CLEAR for their support. So thank you very much, and I think I'm a bit early, but thank you. I'll take questions. Thank you.
Thank you very much, Stefan, for this very nice talk. Do we have questions?
Thank you for a nice talk. Okay. I'm curious what the energy, what was the energy at SPS?
Well, it's the extraction line from the SPS, so I think it's 450 GeV.
So gamma is like 450. Is your saturation impacted by the gamma of your particle?
No, not so much. So at 450 GeV, the field lines are essentially radial. So there's a if you were very non-relativistic, then it would be spread out. So for low energy, you'd smear out the bunch. But these energies, it's basically a relativistic proton bunch. So the field lines are, they're radial. So you have a proper time profile of the bunch.
Does saturation, does the gamma impact saturation?
But perhaps I'm misunderstanding the question. So you mean?
As your fields are compressed, doesn't that drive up your signal into a saturation?
Yes, so as the energy of the bunch increases, the field lines will become more and more radial. And at some point they saturate at radial, but that's actually the working point that we want to be at. We want the beam to be radial, because then we measure the exact charge profile of the bunch due to the radial field lines.
Thank you.
Is that right? Yeah. Okay. Thanks.
Another question?
I wanted to ask over here.
Sorry,
I wanted to ask about the distance between the waveguide and the beam, and also radiation damage issues for the waveguide or for the fiber. What are you using, and how long will it last in real use?
Yeah, those are good questions. So the distance between the beam and the waveguide actually is shown essentially on this plot here. So at the SPS, the crystal was placed 66 millimeters from the beam, but in this case, now we're operating at the in the simulation shown here, this was assuming a 30 millimeter beam pipe radius for the tests that were performed at HiRadMat. That was the beam pipe radius that we were working to, and then the electrode is around 10 millimeters thick, and the waveguide is placed at 40 millimeters. Actually, for the LHC design, it's increased slightly. We changed the location of the pickups from being at the interaction region 4, where the beam height could be slightly smaller, to being closer to the main two experiments near to CMS and Atlas. So the beam pipe radius is now increased to 40, which is the new design. So that's in terms of the radius. We're now operating at 40. In terms of, the other part of the question was about radiation tolerance. And indeed, everything has to be radiation tolerant. Of course, particularly now we've moved to this location close to the experiments. The nice thing about a ridge waveguide structure is that it's not a ion implanted structure that's typical of an electro-optic modulator. It's a ridge waveguide structure which is inherently more tolerant. It's basically just a physical piece of lithium niobate. What we do have to take care about is the glue between the fiber and the waveguide, but essentially that's a NASA-certified radiation-tolerant glue, and we're planning also to do radiation tolerance tests. We've actually used fiber inside the Atlas detector for the alignment system of Atlas, which was a frequency scanning interferometer system based on 842 fiber-coupled interferometers, where we used similar glue and similar fiber to attach a beam splitter onto the end of the fiber. Using UV-cured glue, and this has basically, stood the test of time inside Atlas at the IP. So we're quite confident that the radiation tolerance of the, should be fine. If you use a pure silica-doped fiber, that's basically the trick to getting a good radiation tolerance on the fiber. And of course, the other aspect to mention is that even when it's installed, of course, the pickups are completely replaceable without breaking the vacuum of the system. So if we had to, we could replace the pickup and the waveguide without touching the vacuum of the LHC. Okay, any more questions?
Last question.
Is it Peter?
Peter, you have the mic.
Yeah, thank you very much for this very interesting talk. I would be interesting on the lower current limit of this type of detectors. And as the extreme point would be slow extracted beams, which are very low current. But the advantage is you have a pickup without a lower cutoff frequency. Can you tell us a little bit about the lower limit and what can be done, a very long crystal or whatever?
Well, that's a good point. I know someone in the audience who might be able to help you there. The focus of this project has been on a very broadband high frequency. I think our lower cutoff limit is basically the repetition rate of the LHC. We want to be able to not be perturbed too much by the cycling, but it's possible, of course, with a crystal to make what's essentially a DC measurement of a DC beam. And if you don't care about the high frequency response, you can simply extend the length of the crystal to enhance the sensitivity. And actually, that's exactly what Michael Krupa and Antonio, who's there, have been doing as a project. So I think you're nearing the end of your thesis and have developed a full system that you can. You should connect afterwards about that. But it's a very nice system that's been developed, it's grown out of this project with a focus on DC beams that allows you to access much lower charges, essentially. Yeah.
Okay, thank you very much.
Okay, I think we have to move to the next talk.
Yeah, of course.
Let's thank the speaker again.
Thank you.
The second speaker is Adrian Hoftiger from GSI. During his Bachelor and Master of Science in Theoretical Physics at University of Bern, Switzerland, Adrian studied the effect of global cosmological expansion on local dynamics. Then he worked on the space charge effect and advanced modeling for CERN low energy machines during its PhD thesis at EPFL and CERN. Adrian spent 3 years at CERN as a fellow to work on coherent beam stability, wake fields, and space charge. Since 2019, Adrian is a permanent staff member at GSI and his main domain of activities are the modeling and measurement of collective effects and multi-particle physics, and high-intensity beam dynamics for fair synchrotrons. And the talk is Diagnostics with Quadrupole pickups. Please.
Thanks a lot, Nicola. And thanks most of all to the organizers to invite me to talk about one of my favorite research activities, which is playing with quadrupole pickups. So I'm coming a bit from the beam dynamics side, and that's why maybe on the diagnostic side it will be a bit simplistic, but I invite you nevertheless to ask as many questions as you want. So I left here the abstract for afterwards. The motivation about this whole story is a bit that we want to measure direct space charge strength, so the transverse space charge strength, by looking at the beam size oscillations about the matched beam size, and that gets a frequency shift. That frequency shift you can measure, and that would allow you directly to measure how strong space charge is. There are not so many other methods other than calculating how strong space charge should be from the beam size and the intensity. So this is a very valuable approach, let's say, to understand what the beam sees. So the first order moment of the beam, if you're looking at the bunch, would be what we're looking at in the usual dipole BPMs, where you have the rigid dipole oscillation. And due to Newton's third law, all the particles acting on each other, the forces sum up to 0, and you don't have any direct space charge effects there, at least without higher order projections. And that's why we want to have a look at the second order, and that's the quadrupole or envelope oscillations. And as I said, they are defocused by transverse space charge forces, so they are the oscillations of the beam size, not the centroid. And that's one key point for the rest of the talk. Think about quadrupole pickups and not dipole pickups, yeah? Now, the content will be a bit of an overview of what a quadrupole pickup is and what we did with it in the past decades. There are a few studies here and there. And then during my studies in the recent years, I observed a few new modes that have been theoretically described, but now we see them. And it actually came about that I was looking at the CERN PS, and I saw so many frequency lines in the spectrum that I was like, what's going on? So a few of them, they are identified by now, and I will talk about how they can be useful for diagnostics. So a lot of these things, they are not as used as much today as we could, but I want to convey how interesting this could be. And finally, now that I'm at GSI since a couple of years, we've set up a very nice and clean environment for quadrupole pickup measurements, together with a kicker, so that we are in the position of doing quadrupole beam transfer function measurements. And there were a few questions clarified there on chromaticity and how it affects this width of the envelope mode. Good, so let's start about the overview. So let's have a look at how a quadrupole pickup looks like. Here on the top right, you see a schematics. So you have the transverse cut of the quadrupole pickup. You have 4 electrodes, the top, bottom, left, and right. And here this little beam goes through and has a certain offset. So when we're looking at the induced voltages on the electrodes, we would have the main part that scales with the beam intensity being the common mode or the monopole mode. Then the next order would be the dipole mode. So in the right and left, you have the horizontal part, which is then directly affiliated, as we know, to the dipole moment of the beam. So X would be the dipole moment. D is the distance to the plates. And then in the vertical, you would have the same with the vertical dipole moment. And finally, what I'm interested in then is this quadrupole order. So you need to eliminate the common mode and the dipole mode here so that you really see the quadrupole mode. So that you can achieve by a certain combination then, and the quadrupole mode will directly tell us about the beam sizes. Unfortunately, due to feed down, you will always have certain contributions from the dipole moment as well. But what we really want to see is the beam size oscillation, of course. That's a bit simplistic here. We're neglecting dispersion here. I will come back later with dispersion included, but it's just to drop it here. So we can combine these 4 voltages in a certain way to measure normal dipole beam moments, as we usually do in BPMs where we get the horizontal dipole moment out by subtracting right from left, and the vertical moment from subtracting bottom from top. So you could have a look at the 4 plates with this polarity, plus on the top, minus on the bottom, plus on the left, minus on the right. Or we could combine the voltages to measure the quadrupole beam moment so that we reject all the other common and dipole moments. And that you do by having the same polarity on opposite sides. So plus right and left and minus top and bottom. That's basically the setup. And it's very important that you have this kind of angular dependency, of course, in order not to suppress these nonlinear higher order modes. Good, let's have a look at what happened in the last decade. So this whole story with quadrupole pickup started with Miller at SLAC. That was in 1983. They tried to do some emittance measurements in the time domain. It's really challenging to remove this dipole part there, so they fought with this, and later there was a nice PhD project by Andreas Jansson at CERN and PS with a magnetic pickup structure that was then, by construction, removing the monopole moment, and the dipole moment could then easily be removed. But as a whole story, the time domain is extremely challenging, let's say, and that's why it's a bit more fruitful to go to the frequency domain, where you can separate all these contributions by just looking at different frequencies. So let's have a look at what happened in the frequency domain. There were some emittance measurements done by Tang at Fermilab in 2007, but I'm mainly interested in space charge measurements themselves. And here the first picture on the top right would be the first quadrupole BTF that has been reported by Michel Chanel at CERN in 1996. So you would see here going through the envelope frequency, and you have this nice peak resolved, and that peak frequency is moved away from 2 times the single bad tune, so the unperturbed envelope tune. And this shift you can use directly to measure how strong space charge is. There were further studies afterwards, but all of this was done for coasting beams. So the last one that was done, to my knowledge, was Rahul, who's also here, and Marek and others at GSI in the CIS-18. And that's shown here on the lower right. And that was done with injection oscillations. It's a bit small, but you see the spectrum. And the lowest panel is for low intensity. The highest panel is for high intensity. And while the main peak of the horizontal tune stays, and 2 times the main peak here on the right stays as well, there's a second peak just slightly left to the 2qx peak here, and with increasing intensity that moves towards the left. And that would be the envelope tune. This is a very nice and clean setup with coasting beams. The problem is a bit that we have bunched beams in most situations where we really want to know what's going on. So if you want to use the quadrupole pickup as a diagnostic tool, it should be useful where we are in a critical situation, where we don't understand what the beam is seeing, what's going wrong. So for example, in the case that a synchrotron is limited by space charge, there are certain resonances that are reached because of the strong space charge. That is typically in a situation when you're bunching the beam and when you're running into a critical situation. So we need to work with this pickup in bunched beam situations. But that's quite demanding. So I started studying this a couple of years ago. On the HB 2018, I talked about first quadrupole BTF measurements at the CERN PS, and I will show a few pictures of this afterwards. The idea here was really to look at the space charge shifted, not envelope, single tune, single peak, but bands. Because when we have a bunch, we have changing space charge strength along the bunch, right? So you would have a lot of different contributions along the bunch in terms of space charge. So that becomes a band instead of a single tune peak. And what I observed there was the impact of chromaticity on this width of this envelope resonance. And I discovered the coherent dispersion mode, which was normally described in theory but was not observed so far, and that was rather evident, so it was quite nice. So we can use that for diagnostics again. And the second part I did was presented on the 2019 Zermatt workshop on injection mismatch studies at the CERN PS. And that was quite interesting because I was looking at head-tail instabilities and how the coherent dispersion mode grows with them, so it can be useful in this direction. And I talked about the skew envelope modes that are coming up in the quadrupole spectrum, but you don't see them in the dipole spectrum in the usual BPMs. And they are affiliated to linear coupling. So as I said before, I would now go to the next part, and I would like to talk about the dispersion mode and the skew envelope modes. So these are the newly observed second order modes I was talking about before. Let's start with the skew envelope mode that is affiliated to linear coupling. The beam by itself, it features two odd or skew eigen modes. They are second order resonances, and we all know about them from resonance diagrams, but you can also see them in the beam motion. And that's what I'm talking about. Chernin was the first one to talk about this in conjunction with space charge. And there are these two eigen modes. There's the low frequency eigen mode, that's the difference resonance. So that's mainly Qx minus Qy, the difference between the two horizontal and vertical tune. And the high frequency eigen mode, which is the sum resonance, so Qx plus Qy. And the driving terms for these don't only originate from the skew quadrupole component in the optics when you have a coupled lattice, but also from space charge coupling in case of unequal beam sizes. And that is something that you don't see when you're doing normal dipole BPM studies. So here's an example at the CERN PS injection. That is a spectrogram with the horizontal axis being the time, a few hundred turns after the injection, and the vertical is the frequency of the quadrupole pickup. And you would see in this case here the spectrum, how it looks like when we're injecting into the PS at the skew quadrupoles providing a maximum coupling. So you would see the two main lines here in the center around 0.2, 0.3 frequency, that's Qx and Qy. And then you would see one low mode here, that's the difference, and up there is the sum resonance. So you see them directly identified in the spectrum. And that's one of the key points here. We want to talk about diagnostics. So that can be used as a diagnostic tool. It's a beam-based measurement of the injection mismatch in case of linear coupling. And what you need to do is just to minimize the amplitude in these two lines via skew quadrupoles. Nowadays we're talking a lot about automatic optimization and so on that you can use directly for that. And as I said before, in contrast to dipole BPM-based methods, like for example, when you're changing the tune and you're going through the other tune and you're looking at the closest tune approach, that would not take into account space charge. This method here does, because that's what the beam actually sees. Good, so that's for the skew modes. My screen just went off, so I'm going to turn around. The next part would be the dispersion mode and the affiliated measurements there. So I said I was doing some quadrupole BTF measurements at the CERN PS with a quadrupole exciter. So here that's at a rather low space charge, about 5 times lower than we're used to from LHC beam production. You would see here on the left side the excitation signal. Again, that's a spectrogram, so you see the tune on the x-axis and the time on the y-axis. That's the excitation signal going through. On the right side, you would see the response from the pickup. And you can already see that there are a lot of lines here, and there are distinct peaks around the machine tunes that I've set to something below 0.25. And then you see frequency bands up here that are related to twice the machine tunes. That's the envelope bands we're searching for. Here it was a bit difficult at times because of these instrumentation affiliated noise lines. So therefore it's not simply an FFT that you can take, but you need to do the demodulation to see it properly. So let's have a look at the 3 different spectra taking exactly this experiment. On the left here you see the spectrogram, the same spectrogram as before from the QPU, but using only the horizontal dipole moment. You can see there is some activity around Qx here. Then on the vertical one you see there is some activity around Qy. So they are really separate. And then if you go into the quadrupole order, combining the signals in the appropriate way, you would also see this additional stuff here. That's what we're going for, right? And the moving down of this, so the detuning of this would be directly related to space charge. That's the expectation. So as I said, we would demodulate the signal with the excitation signal, and then you get this kind of result here, where you're going from 0 to 0.5 in tune, and you see the corresponding response along the excitation. Now, you see these two it's a bit unreliable, the screen. I'm sorry you don't see that. But so here we would have the upper frequency band on the top right. That's affiliated to 2 times the vertical tune. and then the horizontal one is down here. And the two lines that I've extracted from up here, the red line is the Qx, the blue line is Qy. We would see that there's an additional peak, if you see that here, that's a bit shifted down from Qx. So that's not directly on Qx, and that's the point here. That's the dispersion mode, and you need to be a bit careful in the quadrupole spectrum because that doesn't sit exactly on the tune, it sits a bit below. So to understand a bit the content of the spectrum, let's have a look at a few simulations of Eigen Modes in the quadrupole pickup spectrum. For the CERN PS here again, same as the experiment conditions. On the left, you would see the picture here for only sigma x squared minus sigma y squared, so the envelope, so the beam oscillations. Here it's for a coasting beam and no dispersion in the machine, and you only see the two peaks that are affiliated to the horizontal and the vertical envelope. Then if you include dispersion in the model, you would get this additional peak down here. That's the coherent dispersion mode. And with this low space charge here, you can still see that the peak is a bit shifted away from Qx. It's a bit lower. That's due to space charge detuning. The coherent dispersion mode, what does it really mean? It's an oscillation about the matched dispersion. So that mode actually measures the correlation between the transverse offset, x and y, and the longitudinal momentum. Okay? And again, negative tune shift with space charge. And then if you include chromaticity, and that was one of the major parts of this simulation work here, simulations showed that with chromaticity, the envelope bands got much wider. So if you're comparing between here and there, they're becoming about a factor 1.5 or something wider, and that's just because of chromaticity adding. So if I want to go back, I want to extract the space charge tune shift, I now need to take also care of chromaticity. And that was a bit of a problem at the time for the CERN PS setup, let's say, because I was doing everything at natural chromaticity. So let's compare the measured spectrum and the Eigen Modes from the simulation in orange. And you can see again that when we're putting them on top of each other, they explain more or less well the range of envelope frequencies, so the width of the envelope resonance. So that means there's a mix of space charge and chromaticity, and that means that it's challenging to extract the space charge tune shift from bunched beam QBTF when you are at natural chromaticity, like in many smaller machines where we are space charge affected. And the second part here was the coherent dispersion mode, as I said. That was just because it was shifted away from Qx. Now, again, key point, we can use this as a diagnostic tool. It's a beam-based measurement of the dispersion injection mismatch, which means that we can again minimize the amplitude in the space charge shifted dispersion, and if you're looking closely, you will see two peaks, the dispersion mode and the normal Qx mode. So like this, you can really identify which one is the dispersion mode. And for example, we had an experiment where we were matching dispersion from the transfer line into the PS, and we were looking at the normal dipole BPM stuff. But with this method, I could see that we are not well matched. There were parts missing because space charge is not taken into account all of these things. So that could be an approach for space charge dominated or very strong space charge case machines, where you can take a beam-based measurement to measure this much better. Now, again, in contrast to dipole BPM, as I said, this method includes space charge. And then the second part of this dispersion mode was the observation with the head-tail motion. So the CERN PS normally runs at natural chromaticity, and it features higher order head-tail instabilities. They are intrinsically unstable beams at typical intensities, which makes it a bit difficult to just go to zero chromaticity, right? Because then the instability becomes much stronger. Now, it can be cured with a new transverse feedback that was installed, and here on the lower left you see the same spectrogram again that we had seen so many times already, frequency range and time in the vertical. And you see here that there's a strong contribution or a strong amplitude around the Qx in the dispersion mode here. On the right side you would see a wideband pickup, and the top here is the difference signal for the horizontal, and you can indeed see that there's some pattern developing, some head-tail instability. In this case, it's not symmetric, it's developed towards the back, and that's because of space charge. So there are a few open topics currently discussed. But let's say if I then go and cure it with a transverse feedback, I can see in the quadrupole spectrum that correspondingly the amplitude goes down, and in the wideband feedback, of course, the instability is gone. Now, why am I showing this comparison here? Watch closely. 2 times the Qx is deflected on 0.5, so that would be the deflected line. That is the dipole moment, 2 times Qx. And that's much weaker than the dispersion mode. So you can really see that the strong content in this line is not because of the dipole moment getting stronger, but it's because of the dispersion mode that measures the correlation between the horizontal offset and the longitudinal momentum. So that's opening interesting new opportunities. So the head tail instability correlates the horizontal offset with the longitudinal momentum. And we see a strong signal at the coherent dispersion mode near Qx, while the dipole mode to Qx is only faintly visible. So you can use this again and discriminate. So to me, this looks like a very promising diagnostic tool to further investigate and understand better the topic of head tail instabilities versus space charge. Because there are a lot of open questions in this direction, and a lot of the theory that is known and works well only works without space charge, which is not the case at most lower intermediate energy synchrotrons. Good, so for the final part, let me turn to the new GSI measurements that we've done this year. And as I said, the setup is a bit nicer to what I had before because it's cleaner for low intensity ions, so we're not affected by all these nice beam dynamical things going on in the CERN PS. Which makes it a bit simpler to understand finally. What about this chromaticity impact on the envelope resonance? As I said, it widens up. At the CERN PS it's a bit difficult to correct chromaticity because of the head tail instability, but here we can do that. So let's have a look at the setup. And again, it's gone. The quadrupole BTF experiment that I was setting up there used a quadrupole exciter. Here on the right, you see a picture of the Cis18 with the quadrupole exciter located in sector 4. And the quadrupole pickup located in sector 12. It has a power delivery of maximum 400 watt and a peak voltage of 3 kilovolt peak to peak. That is similar to the CERN setup, maybe a bit stronger. And the frequency range it covers is 100 kilohertz to 2 megahertz. That was kindly set up by all the colleagues in the beam diagnostics group. And what I did, so first of all here, you see the beta functions around the machine. And the quadrupole exciter is located close to the horizontal focusing magnet, which means that the beta X is much larger than the beta Y. So the action will be stronger in the horizontal. That's why we see the horizontal afterwards. It's just to know already. Now, I went to flat top, a low energy flat top with lead ions. And that meant that I have almost vanishing space charge. So I can really study what happens switching on or switching off chromaticity in a way. I set tunes such that the horizontal and the vertical tune fractional parts are far away from each other. So 4.1 is the horizontal, 3.22 is the vertical, and that means that the envelope tunes, the unperturbed ones, should be around 0.2 and 0.44. So I get all the frequency contributions separated from each other. That makes it simpler. And then I just went for a quadrupole excitation sweep from 0.05 to 0.45. And as I said, it's no head tail instabilities with the ions at the Cis18 intensities, which means I can correct chromaticity to 0 without problems. While if I do that at the CERN machines, I would get all the beautiful head tail instabilities, and it's really difficult to study. Now let's first look at a couple of simulations here. On the left side here, we have the natural chromaticity. You would see on the top the spectrogram of the excitation. Horizontal axis is the tunes, vertical is the frequency. And we hit the 2qx and 2qy around the red line here, and then afterwards at the blue line there. The next panel here is the response in the pickup. And there you can see that mainly you see some part in the horizontal. And then what we are not really able to completely resolve in the measurements, of course, but in the simulation I can see it. Here you see the horizontal beam size starting to oscillate, growing in emittance, and then settling down at a 50% larger beam size. And in the vertical, it's the same, but around the second resonance here, 2qy. Now, if I correct chromaticity to 0 in the simulations using sextupoles, I can see that the response here becomes narrower in time. And the same goes for the for the tune range here. It's a bit difficult to see, it's just to give you a bit the idea here. But zero chromaticity features narrower response, and that's what I want to look at. Do we see this in the experiments? So if I compare the parts here, on the left, the projection onto the tune, and on the right, the projection on the tune. In blue, you see the zero chromaticity, and orange, the natural chromaticity. Then you see that the peak becomes much narrower when you're removing chromaticity. So that's what I want to see in the experiment now. I'm showing once more nice spectrograms. So here the measurements with quadrupole BTF have a 50 millisecond sweep time at 80 watt. Natural chromaticity. At first I looked at the horizontal and the dipole spectrograms. So you would see first here the horizontal reaction, then the vertical reaction there. I can project these down and get the actual tunes here. So that's 4.13 in the horizontal and 3.21 in the vertical. So now I know my tunes, and now I look at what happens during the time that I'm exciting. Here on the top left you see a plot of the DC current transformer. The entire cycle is displayed here, but the relevant part is the gray area here. That's when I'm starting the sweep, and I'm going through, and you can see that there's a drop in intensity, or in green in the current here. If I look at the ionization profile monitor at the same time, first of all here during the ramp I can see that there's adiabatic damping, so it goes down. And then during the part here, you see first the horizontal beam size going up, and then the vertical a bit at the end. That looks very promising. So if I'm looking a bit closer, I can have a look at the sum signal of the 4 electrodes in the pickup. That matches pretty much the losses that I'm seeing here on the left side in the DCCT. And here on the lower panel, I extracted the corresponding measurements of the beam size, and you see that the first drop here is really related to the horizontal beam size increase, and the second drop to the vertical beam size increase. So very nicely, we can take the two apart, and the excitation works exactly as we expected. Now I'm looking in the response in the quadrupole spectrum here, and I can extract it again, and there I get my nice QBTF measurements. Here on the left, I can just simply take the FFT now, because there were not so many instrumentation-based lines. And you see in red here the horizontal envelope band at finite chromaticity. If I do the demodulation, you see it a bit better here, but there's more noise floor on the sides, let's say. But you see, if you zoom in, that the width of this is about 0.027, or full width half maximum of 0.012. So that's not so far away from the simulations. Now the big question, of course, is what happens when I correct chromaticity now? And you can see if I do the same evaluation here, the peak in blue becomes much narrower. And that's exactly what I wanted to understand. Space charge is almost no issue, as I said, it's 10 to the minus 4, so that fits in about. And the chromatic part was really the major contribution to the width of this envelope resonance. So perfect, we understand this, is finally confirmed on the experimental side. And that leads me to the conclusion that if we want to measure space charge with bunched beam, we should go to zero chromaticity, because then we eliminate the chromatic influence on the resonance width. Good, so let me conclude finally. Quadrupole pickups can provide non-invasive beam measurements. If we are very careful with excitation, it doesn't lead to a lot of blow-up as well. For example, at CERN I had only 5% emittance growth, so that works very well if you're careful. They require a nonlinear pickup structure, so it doesn't work with shoebox type pickups, for example. Frequency domain in general works better than the time domain, and we get useful mismatch information in the quadrupole spectrum out of this. So I talked about the skew envelope modes that provide information about linear coupling. There are the dispersion modes, which measure the transverse to longitudinal momentum correlation, and that is useful for either dispersion mismatch or for observing the head-tail instabilities in a different way. And then there's the original idea of the whole study, that's the even envelope modes, and that's the Betatron mismatch when you're going into the machine. And then typically the second order modes modify with space charge, which doesn't happen on the dipole order, and therefore frequency is detune of these modes. And I can have a look at the mismatch oscillation amplitudes, which then include space charge mismatch. So that's a beam-based measurement including space charge. And that allows me to measure space charge strength, for example, at zero chromaticity. And finally, the part that I showed with the Gsi measurements, they confirmed the chromaticity broadening of the envelope mode width, and the next steps clearly are, let's do this again at lower energy, and then really observe how this scales with space charge. And that brings me to the end. Thank you very much for your attention, and thanks again for the organizers to invite me. And I have to say acknowledgements to all the GSI colleagues from the beam diagnostics department, especially Rahul, who is sitting here in the room and who did a lot of these measurements together with me. Thank you for listening.
Thank you very much, Adrian, for the very nice measurements. And sorry for the technical issue with the screen.
No problem.
We have time for 1 or 2 questions.
There was a bit more physics involved than the talks before, I'm sorry.
I don't see any. I have one. Ah, yes. Over there.
Yes, please.
I was wondering, would it be interesting then to go to octopolar pickup? Could we gain something with that?
Very good question, thank you. I have complete separate interest in simulating higher order moments and looking at that. And from that I see that the octopole order is typically Landau damped. So it's extremely difficult to get information out of that. And since the quadrupole moment is the first order where we see space charge, and that was the original idea to measure how strong that is, I was focusing on that. And that's the order, the coherent order, that is just in about not Landau damped. Sextupole order is Landau damped, octupole order is Landau damped. So if you want to excite these with a dedicated sextupole or octupole exciter, you need to provide a lot of amplitude, and at the same time it becomes more and more difficult because these higher orders, they have a lower transfer, let's say, of energy to the beam. So one could think about it, but at the moment I don't see the application there, and it can be really, really challenging, I think. Thank you.
Other questions? In the design of your pickups, do you use standard pickups, or would you recommend to have particularities for the pickup design, the positions of the
so at
pickups?
CERN we had stripline pickups because of the high currents. That was a very nice way of seeing everything. Now at GSI, with the lower currents, we can just use, let's say, in a way, regular BPMs. But the point really is that you need to have this angular dependency, right? If you don't get that, then the design doesn't support measuring the quadrupole pickup. But in general, it's something that I can imagine to just add, and as it was done at CERN actually, to add the quadrupole channel as a readout to the usual BPMs that we have at many machines. If you have both horizontal and vertical plates, why not also extract the quadrupole information? And then you sit a student on that and he extracts all the nice, beautiful information. So there's no big showstopper because of big designs or challenging things. It's quite straightforward, actually.
Okay, thank you. Let's thank Adrian again.
Yeah, thank you.
So we are moving to the third talk from Shiro Takano of Spring 8. Shiro Takano is a physicist with a doctorate of science from Tokyo University in Japan for his studies in X-ray astronomy in 1990. After getting the degree, he joined the storage ring FEL group at the UV synchrotron radiation facility in Japan. He achieved the first lasing of the UV storage ring in 1992. He then moved to the Spring 8 synchrotron radiation facility in his construction phase. He has been in charge of beam diagnostic instruments. Since 2017, he has been a leader of the beam dynamics and monitor group at JAS3, which is in charge of the operation and maintenance of Spring 8. Shiro is now involved in the accelerator developments for the upgrade project of Spring 8 2. And his talk this morning is beam-based calibration of sextupole magnet displacement with Betatron tune shift. Please, Shiro.
Thank you, Chairman, for introducing me to the audience. I'm very happy to be attending the IBIC conference again in person here in Krakow. Today, I'm going to talk about beam-based calibration of sextupole magnet displacement with Betatron tune shift. I would like to thank the organizers for giving me this opportunity. This is the outline of my talk. After a brief introduction, I would like to have an overview of theoretical background of our beam-based calibration method. And then I would like to elaborate on feasibility studies on the spring-age storage ring. Before closing my talk, I would like to mention some issues and challenges. The alignment of The alignment of sectoral magnets is one of the critical issues for the upcoming fourth-generation light sources and future colliders to ensure enough dynamic aperture for stable operation and minimize deterioration of beam quality. A sectoral magnet horizontally or vertically displaced from the beam exert a normal or skew quadrupole Q field. We propose a beam-based calibration BBC method for the sexpole magnet displacement by observing the Betron tune shift. The beam position that makes the horizontal and vertical Betron tunes invariant to the sexpole strength marks the magnet center. So let's get started with the theoretical background of our beam-based calibration method. Suppose that a beam passes in a sexpole magnet with offset x0, y0 from the center. When the beam moves delta x, delta y around this point, the magnetic field at the destination point can be represented by these formulae. Here, B double prime represent the gradient of the sexpole magnet. The second and third terms in this formulae represent the normal quadrupole component and skew Q component in the magnetic field, respectively. So the beam passing in a sexpole magnet with a horizontal offset undergoes a normal Q field, and the beam with a vertical offset undergoes a skew quadrupole field. The skew quadrupole field derives the linear Petalum coupling delta C that adds to the indigenous coupling driving term of the whole ring. If we suppose that the sexpole strength is changed by delta B double prime, then the tune shift can be represented in this formula. The first term represents the tune shift due to a change in normal Q field of a horizontally displaced sexpole magnet. The change delta C in the linear coupling by a vertically displaced sexpole magnet varies the overall coupling driving term of the ring, which eventually changes the Betron tune. For Betron tune under coupled Betron motion, refer to the paper by one of my colleagues, Takao. To lowest order of delta C, the tune shift can be written in these forms. Now I'd like to move on to the principle of our Betron tune-based sexpole center calibration. The beam position x0, y0 fixing the tune under sexpole change can be represented by these formulae. If we suppose that the horizontal and vertical Betron functions at the target sexpole magnet are different, the two loci or trajectories for the tune fixing points intersect only at one point at the magnet center of the sexpole magnet. I'd like to give you some remarks about the Petalum coupling. In the small coupling limit, information on the vertical center of a sexpole magnet is totally missing in the tune shift. In that case, Sextupole horizontal center is knowable by observing either the horizontal or vertical tune. The key point to successful sextupole beam-based calibration on real rings with a finite coupling is Petalum coupling control to enhance sensitivity to the vertical displacement. So feasibility studies with increased Petalum coupling were planned at Spring 8. With beam parameters in normal operation, the separation of the two lossy for tune fixing points are not good enough for precise calibration. After increasing the Petalum coupling, we can get larger separation of the two lossy for tune fixing points. Sorry, I can't move forward. Sorry. So we conducted feasibility studies on the Spring 8 storage ring. The Spring 8 storage ring is an HGV photon source ring. The circumference is about 1,400 meters. For the target of the beam-based calibration, a sextupole magnet placed in one of our 30-meter long straight sections was employed. That has a beam position monitor, BPM head nearby. The beam position at the target sextupole magnet was controlled by using local orbit bumps. Actually, there were two other sextupoles in the orbit bumps, which are used in normal operation of Spring 8. They were temporarily switched off for the experiment. It doesn't work. Oh, thank you. It's okay. The targets, the BPM nearby the target sextupole is read by a recently developed micro-TCA.4 based BPM electronics. The COD block of the electronics generate turn by turn, fast at 10 kHz and slow 10 Hz COD data. For details of our BPM electronics, refer to the previous presentation at IBIC 2019 by one of my colleagues, Maesaka. During our experiment, fast COD data were sampled at 10 kHz with submicron resolution. Oh, sorry. Two sets of bunch-by-bunch feedback and diagnostic signal processor, IGP12, were employed. Two bunches out of the stored 21 bunches were subject to real-time tune monitoring, one for the horizontal beta tone tune and the other for the vertical beta tone tune. The single bunch phase tracker capability integrated in the signal processor provided real-time tune monitoring with 10 to the minus fifth precisions with 5 Hz sampling during the experiment. We temporarily increased the Petalum coupling by using the Skew quadrupole magnets integrated into the storage ring. The coupling driving term is a complex number. The total coupling driving term can be represented by the original coupling driving term of the whole storage ring and that added by the Skew quadrupole magnets. First, we observed the projected vertical beam size varying the argument of the Skew coupling. Sorry. The vertical size can be related to the argument of the Skew coupling by this formula. The value of the argument of the Skew coupling maximizing the total coupling was found, and the argument of the original coupling driving term was experimentally determined. Hereafter, we fix the argument of the Skew coupling at this value. Next, we evaluated the magnitude of the original coupling, varying the magnitude of the Skew coupling. The magnitude of the original coupling was evaluated to be 0.008. And then we set the magnitude of the Skew coupling at the maximum available value of 0.05. That led to the magnitude of the total coupling of 0.048. And extra gain for the sensitivity to the vertical sextuple displacement was obtained by manipulating the tune difference. For the feasibility studies, we temporarily changed the vertical Betatron tune from 19.325 to 19.225. So the sensitivity enhancement is calculated to be 13-fold. So overall sensitivity was improved by a factor more than 10 for the proof of principle experiment at Spring 8. The measurement procedure in our proof of principle experiment is as follows. Step 1, set a vertical orbit bump. And step 2, sweep the beam horizontally, monitoring the beam position and the Betatron tune with the target sextupole off and on. And step 3, set other vertical orbit bumps, repeat step 2. And 4, find beam positions xy, y1, and x2, y2, fixing the horizontal and vertical Betatron tunes respectively. Now let's have a look at the result of our experiment. When the beam passes at the sextuple magnet center, both the horizontal and vertical Betatron tunes are invariant to the sextuple strength. The center of the target sextuple magnet was successfully marked by the intersection of the fitted loci of measured tune fixing points. And precisions of a few tenths of microns were evaluated from the fitting residuals. BPM offset to the target sextupole was also successfully figured simultaneously. Let me compare the result with the theory. We calibrated the Betatron function at the target sextuple magnet with observed tune shift due to normal Q contribution. Theoretical loci for Betatron tune fixing points are represented by this formula. The measured tune fixing points are shown here after subtracting the BPM offset. The measurement was in good agreement with the calculated loci of tune fixing points. So, principle of Betatron tune-based sextupole beam-based calibration was demonstrated in quantitative agreement with the theory. Before closing my talk, I'd like to mention some issues in the feasibility studies and challenge. Vertical tune for sextupole off was dependent on the horizontal beam position, so influences of residual field in the sextupoles involved in the orbit bumps or orbit bump leakages needs to be checked out. And at the target sextupole magnet, the vertical beta function was smaller than design. So examinations of Betatron function or So examination of Bertrand function distortions over the storage ring would be necessary. Challenge will be a practical application to the entire circuitable magnets of the storage ring. So future studies will be considered employing faster beam orbit manipulation, i.e. by AC exciting the steering magnets, and faster Betatron tune tracking to complete the measurement in a short time. Let me wrap up. A beam-based calibration BBC method with a Bertrand tune shift for the circuitable magnet displacement is proposed. The feasibility studies at Spring 8 successfully demonstrated the principle for both horizontal and vertical sextuple displacements in quantitative agreement with the theory. The measurement resolution of 10 micrometers will be feasible with further improvements. To apply the entire sextuple magnets in a storage ring for practical use, it's necessary to complete the measurement in a short time. So future studies will be considered employing faster beam orbit manipulation and Betatron tune tracking. Well, this brought me to the end of my presentation. Thank you for your attention.
Thank you very much, Shiro, for the talk. Do we have questions?
Thank you for the great talk. I have one question is, when you put the sectable changes, do you try to use the signal from BPM data to see the Betatron oscillation changes because of the quadruple item?
Sorry, can you say that again a bit more slowly?
Sure. So the sectables, when you change the beam off center in the sectables, it introduces a quadrupole error. And this can also excite the Betatron oscillation. Have you ever think about the use Betatron oscillation?
We measured data after Betatron oscillation is damped.
Oh, what I mean is a beta function distortion. The optics, beta function distortion because of this quadrupole error.
Regarding the effect of target sextupole, the calculated Betatron distortion is not so large, was negligible. Does it answer to your question?
Yes, thank you.
Another question? No? I have one. At the moment, how long does it take for one measurement for one sextupole?
Well, in a proof of principle experiment, we swept the horizontal beam position by about 1 millimeter, and we took some 10 seconds for one scan for now.
So not so much, but with the number of sextuples that you will have.
Pardon?
It's not so much, but with the number of sextuples that you will have on the low emittance ring, you need to decrease this value.
Yeah, to apply to all the sextupoles in the whole storage ring, we need quick measurement, of course.
Okay, if there is no more question, let's thank Shiro again.
Thank you very much. Thank you.